In this section, we will discuss a special kind of sequences for which, without knowing specifically what that sequence is, we should be able to tell whether the sequence is going to converge or not. And to this end, let me give the following definitions. Definition number one. So definition number one. A sequence Sn is called increasing if every next term in the sequence is going to be larger than the previous term. So if Sn plus 1 is greater or equal than Sn for all n greater or equal than 1. Likewise, second definition, basically symmetric to this one. A sequence Sn is decreasing if now each next term is smaller than the previous term. If Sn plus 1 is less or equal than Sn for all n greater or equal than 1. Then if a sequence is either decreasing or increasing, the common name for this is going to be that the sequence is monotone. So if I'm saying that I have a monotone sequence, it means that I have a sequence which is either always increasing or always decreasing. So then the sequence is monotone. Also, if the inequalities greater or equal or lesser equal in the definitions above are replaced by strict inequalities, then we're going to say so by strict inequalities. So for example, Sn greater or equal, Sn plus 1, sorry, greater or equal than Sn is replaced by Sn plus 1 is strictly greater than Sn. Then we would say then the given sequence is either strictly increasing or strictly decreasing. So let me just rephrase this. So is strictly increasing or decreasing. And now, if we look at particular examples, so let's say example number 1. Let's suppose that Sn is equal to 1 over n. Then if I want to decide if the sequence is increasing or decreasing, I have to compare Sn plus 1 to Sn. So then, for any n greater or equal to 1, if I take Sn plus 1 minus Sn, this will be equal to 1 over n plus 1 minus 1 over n. We can simplify this expression. N minus n plus 1 over n times n plus 1. This is equal to minus 1 over n times n plus 1 once we cancel n. And this is less than 0 for any n. So therefore, Sn plus 1 minus Sn is less than 0, or Sn plus 1 is strictly less than Sn. So then the conclusion, Sn is the sequence Sn equal to 1 over n is decreasing, and because we have less sign and not less or equal sign, then it is strictly decreasing. And of course, because it is decreasing, then it must be the sequence Sn is monotone. Example number 2. Now let's suppose that Sn is equal to n squared. Then, for any n greater or equal than 1, once again, if I compute Sn plus 1 minus Sn, this will be equal to n plus 1 quantity square minus n squared. And therefore, if we simplify, this is n squared plus 2n plus 1 minus n squared. N squared goes away, 2n plus 1, and this is always strictly positive when n is greater or equal to 1. So as a result, we conclude that Sn plus 1 minus Sn must be positive. And if we add Sn to both sides, Sn plus 1 must be greater than Sn. So this sequence is strictly increasing. Another example. Let's look at Sn is equal to minus 1 to the power n. right? In this case, we get a sequence that looks like this. It's going to be -1, 1, -1, 1, etc. S2 is bigger than S1, S3 is smaller than S2, so we keep going up and down in this case, so this sequence is neither increasing nor decreasing, so we can just say that the sequence is not monotone. Example number 4. Let's suppose that Sn is equal to 1. It's equal to 1 for all n greater or equal than 1. Then, if I take Sn plus 1 minus Sn, this is always equal to 1 minus 1 equals 0 for all n greater or equal than 1. And that, of course, means what I'm doing here is fairly trivial. It means that Sn plus 1 is the same as Sn for all n greater or equal than 1. But then, from this, I can conclude that Sn plus 1 is less or equal than Sn for all n greater or equal than 1. Right? Because being less or equal allows being equal. So it's not wrong to say that Sn plus 1 is less or equal than Sn in this case, because saying less or equal covers possibility of being equal. And likewise, Sn plus 1 is greater or equal than Sn for any n greater or equal than 1, because again, being greater or equal includes the possibility of being equal. So what we have is that the sequence Sn from the first inequality, the sequence of Sn is going to be monotone decreasing because Sn plus 1 is less than Sn, less or equal than Sn. So Sn is decreasing. And from a second inequality, Sn is also increasing. So that means that the constant sequence can be thought of as being increasing and decreasing at the same time. And vice versa. So let's call this part A. Part B. Suppose that I have a sequence Sn, which is both increasing and decreasing. What does it mean? It means that Sn plus 1 is increasing, means Sn plus 1 is greater or equal than Sn for all n greater or equal than 1. And that it is monotone, that is decreasing, means that Sn plus 1 is less or equal than Sn, again, for all n greater or equal to 1. But if Sn plus 1 is less or equal than Sn and greater or equal than Sn at the same time, therefore we can conclude from this then Sn plus 1 is equal to Sn and that is for any n greater or equal than 1. And so this means that what we deal with is going to be a constant sequence. So therefore, Sn is a constant sequence right, because we just discovered that all terms of the sequence are going to be equal to each other. Example number 5. Is a sequence let's say Sn equal to 2n plus 1 over n minus 2. By the way, in this case, n obviously cannot be equal to 2, so it means that I have to start the sequence from n equal to 3. So n greater or equal than 3 is a sequence monotone. How am I supposed to decide? I need to use the same idea as I just used in the previous examples. I'm going to consider the difference Sn plus 1 minus Sn, and if this difference has a particular sign, Sign, then I can conclude from that if the sequence is increasing or decreasing. Now, who is Sn plus 1? It's 2 times n plus 1 over n plus 1 minus 2. And Sn is 2n plus 1 over n minus 2. And so now I need to determine the sign of this. To determine the sign, I better put things on the common denominator. So this would be equal to, if I simplify the numerator here, if I distribute 2, so I get 2n plus 2 plus 1, so it should be 2n plus 3. So I have 2n plus 3 times n minus 2 minus the denominator here, n plus 1 minus 2 is n minus 1, so minus n minus 1 times 2n plus 1 divided by the product of two denominators, so that would be n minus 1 times n minus 2. We continue by simplifying. Distribute, factor out things on the top. 2n squared minus 4n plus 3n minus 6 minus 2, let me put this in parentheses, minus 2n squared plus n minus 2n so plus n minus 2n minus 1 of the same denominator, n minus 1 times n minus 2. And so if I look on the top, 2n squared is gone. I have minus 4n plus 3n minus n plus 2n. So minus n plus n. So that is also gone. So minus 4 plus 3 minus 1. There is a minus sign in front, so minus 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 plus 2n, and then minus 2n. minus 2n plus 2n, right? So that is 0. And then minus 6 plus 1, so minus 5 over n minus 1 times n minus 2. And I assume that n is greater or equal than 3. So if I look at the denominator, n greater or equal than 3, n minus 1, and n minus 2 are both positive. 5 is positive, but there is a minus sign in front. So therefore, this quantity is going to be always less than 0 whenever n is greater or equal than 3. And that's the only range of n that I'm going to consider. So then if a difference of Sn plus 1 and Sn is less than 0, so then we conclude that Sn plus 1 is going to be less than Sn if n is greater or equal than 3. And so the sequence that I'm considering is going to be decreasing according to the definition of a decreasing sequence. Okay, so that's one way to decide if a given sequence is increasing or increasing, is to take a difference between two consecutive terms. There is also a second way which uses the ideas that we have not discussed yet in this class, but which you surely are familiar with from the regular calculus. So example 5, let's say I want to decide this. Is the sequence Sn equal to e to the power minus n squared monotone or not? So once again, either I can try to take a difference between two consecutive terms and see what I'm going to get. So number 1, let's take Sn plus 1 minus Sn. That's going to be e to the minus n plus 1 squared minus e to the minus n squared. So how would I deal with that? I can try to pull out a common factor. In this case, a common factor is going to be, for instance, e to the power minus n squared. So this will give me e to the minus n squared, and I'm going to use properties of exponentials. Then I'm going to get e to the minus n plus 1 squared. I pulled out e to the minus n squared, so I need to add n squared to the power here, and then the whole thing for the second guy is just going to reduce to 1 because I pulled out e to the minus n squared. Okay, so e to the minus n squared exponential function is always greater than 0. So this term is always positive. So then the sign of Sn plus 1 minus Sn is determined by this parenthesis. So what can I say here? Obviously, I can try to simplify the power in the exponential. So e to the minus n squared. E to the minus n plus 1 squared is, if I distribute, e to the minus n squared minus 2n minus 1 plus n squared minus 1. And in the power here, I have minus n squared plus n squared. Those go away. So e to the minus n squared, e to the minus 2n minus 1 minus 1. What I know about e to the minus 2n minus 1, the power is strictly negative, right? Minus 2n minus 1 is a negative number. And from the properties of the exponential, we know that e to the negative power is always going to be a number less than 1. And then less than 1 minus 1 is negative, times e to the minus n squared, which is positive, the outcome that this is negative. And so Sn plus 1 is less than Sn for any n greater or equal than 1, and therefore the sequence Sn is strictly decreasing. Another possible way to prove the same thing is to do the following. So we have Sn equal to the minus e to the minus n squared. Therefore, if I have a function e to the power minus x squared, it follows that my Sn is equal to f of n. So it would be enough to prove that this function f of x is decreasing, and if it is decreasing always, then certainly the discrete values that I take along the graph of this function should be also decreasing. All right, so we're going to decide to check if f is increasing or decreasing. How can I do that? Now, f is a continuous function, not a function of a discrete variable. So then I can take its derivative. F prime of x is going to be e to the minus x squared product chain rule times minus 2x. So minus 2x e to the minus x squared. And of course, exponential is always positive. In this case, I'm looking at x. I'm looking at n that are positive, so I'm only interested in x that is positive. So positive, 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 negative. So the entire expression must be negative as long as x is greater than 0. And so, because derivative is negative, it follows that f is strictly decreasing when x is positive, and if a function f is strictly decreasing, again, the discrete values that I take along the graph of this function also must be strictly decreasing. And so Sn is strictly decreasing. So that is something to keep in mind in the future. If I want to check if a given sequence is monotone or not, I either take a derivative of a corresponding function, or I estimate the difference between two consecutive terms of the sequence. All right, so now let's look at some properties of the monotone sequences. Why do we actually single out these sequences? And for that, let's look at the examples that I just proved. So in the first example, Sn was equal to 1 over n, right? And the sequence was strictly decreasing. So that's a sequence which always goes down with n. And I also know that Sn, in this case, are always positive. So if I have a positive sequence of decreasing numbers, then the numbers go down, but they can never become negative. So that means that they don't really have a choice. They must accumulate somewhere, right? Because they don't have a capability to continue going down by a significant amount forever, right? Because they're bounded from below, then the amount by which the sequence goes down with each increased n should decrease. And the sequence should have a limit. And indeed, in this case, the limit of 1 over n is 0. Okay, now we look at Sn equal to n squared. N squared, again, is a positive number, always. So that means that the sequence is bounded by 0 from below, right? And the sequence is not bounded from above because n squared can get arbitrarily big. So if I have an increasing sequence which gets arbitrarily big, then it doesn't take a long time to figure out that in this case, I do not expect the sequence to converge to a finite number, but rather in this case, I would expect that the sequence will go to infinity. In the third example, the sequence is not monotone, minus 1, 1, minus 1, 1. So the sequence is oscillating between minus 1 and 1. So in this case, I'm not going to expect that it will have any limit. So not a monotone sequence, might not have a limit in this case. The last example 4, actually, wasn't there another example here? Okay, so not the last example. In example 4, I have a constant sequence. Again, it's monotone increasing, monotone decreasing. And it's bounded both from above and from below by 1, for instance. And the sequence does have a limit again. In example 5, 2n plus 1 over n minus 2, this sequence is clearly, we prove that the sequence is decreasing, right? So it's getting smaller and smaller. And because n is greater or equal than 3, numerator is always positive, denominator is always positive. So that means that Sn is bounded from below by 0, right? It's always positive, and it is decreasing. So in that case, what do we expect? We expect, again, that the sequence is going to have a limit somewhere at some point, which is at some value which is greater or equal than 0, because it cannot continue going down, right, as an increase. It can continue going down, but it should be by a smaller and smaller amounts, and then the values of the sequence should accumulate somewhere. So then the overall somehow impression that we get from these examples is this, that if you have a sequence which is monotone increasing and bounded from above, you would expect that this sequence has a limit. Or if you have a sequence which is monotone decreasing and bounded from below, then that sequence again will have a limit. If a sequence is monotone increasing and not bounded from above, then we would expect that the terms of a sequence will become arbitrarily big, which means that the sequence goes to infinity. And similar for unbounded from below decreasing sequences. And so this is the intuition that we have to prove now. Let's call this theorem number 1. Any increasing sequence Sn that is bounded from above has a limit. Or rather, which is the same thing, I'm just going to say that the sequence converges. How can we prove something like this? So let's try proof. So I'm talking about a sequence which is bounded from above. So that means that this is actually, if I think of a sequence as a set, I have a set that is bounded from above. If I have a set which is bounded from above, then the first thing that comes to mind is that completeness axiom says that the supremum of this set exists. So since Sn is bounded from above, then as a set, Sn has a supremum. And I'm going to denote this supremum maybe by L. Supremum of Sn is equal to L. Okay, so then what do I know? I know then, number one, it follows that Sn would be less or equal than L for all n greater or equal than 1, right? Because L is a supremum. And in particular, from this, it will follow that Sn is less or equal than L plus epsilon for any epsilon greater than 0, right? So if Sn is smaller than some number, then Sn surely is smaller than that number plus epsilon. Okay, so now I'm going to fix n epsilon greater than 0. So I do know then that this inequality holds for that epsilon in particular. Okay. Now, because L is the supremum of Sn, we have that L minus epsilon is not a lower bound, not an upper bound, sorry. Right? If L is a supremum, then anything smaller than the supremum is not an upper bound. And what does it mean that it's not an upper bound? It means that I should be able to find an element of my sequence which is going to be larger than L minus epsilon. So therefore, there exists an S, I'm going to call S capital N, such that S capital N is greater than L minus epsilon. Right? So there exists an element of my sequence, element of my set, which is greater than L minus epsilon. All elements in the sequence are labeled according to their index. So I found some element which is greater than L minus epsilon, and I'm going to denote its index by capital N. Okay, so also we know that Sn is an increasing sequence. And because Sn is an increasing sequence, then I surely have that Sn is greater or equal than S capital N for any n bigger than capital N, right? If the sequence goes up, then subsequent terms are going to be larger than the previous terms. So if I take index which is larger than some initial index I was looking at, in this case capital N, if I take S with any index larger than capital N, because the sequence is increasing, I expect that S little n is greater or equal than S big N. But I know that S big N was chosen in such a way so that S big N is greater than L minus epsilon. So then by combining these two inequalities, right, S little n bigger or equal than big S, S big N, and S big N is bigger than L minus epsilon, I conclude that S little n is going to be greater than L minus epsilon for all n greater than capital N. And so now I have two things. I have that this inequality holds for any n, and I have that this inequality holds for n bigger than capital N. So then overall, we can say that L minus epsilon is less than Sn, less than L plus epsilon if n is bigger than capital N. Which is the same thing as saying Sn minus L is less than epsilon, is less than epsilon and bigger than minus epsilon if n is greater than capital N. But then I can write that by using absolute value of a sign as Sn minus L, absolute value is less than epsilon if n is bigger than capital N. So what have I got? I picked an epsilon greater than 0. Then there exists an index capital N such that Sn minus L is less than epsilon if n is bigger than capital N. But that's a definition of the fact that Sn goes to L as n goes to infinity. So L is a limit of Sn. So let me write this down here. So therefore, limit n goes to infinity of Sn is equal to L by the definition of the limit. Okay, so I hope that this is clear. And then in the same way, we can establish a different theorem. The following theorem, which is a mirror image of a theorem we just proved. So any increasing sequence bounded from above should have a limit. So the new theorem is that any sequence Sn that is bounded from below and monotone decreasing also has a sequence. So any decreasing Sn that is bounded from below also converges. Okay. And then I can combine the two theorems into the following statement. So the proof of this theorem 2 is going to be exactly the same as a proof of theorem 1, with an exception that signs of inequalities everywhere would have to be switched. So we can combine two theorems into one. Any monotone bounded sequence converges. Right, because if I say I have a monotone sequence, that means that it is either increasing or decreasing. And if I'm saying the sequence is bounded, that means it's bounded both from above and below. So this will cover both possibilities of theorem 1 and theorem 2. And so this is the final result that we proved. Before I do any examples, let me actually prove a couple more, or again, I'll prove one more theorem, and then we'll have a symmetric version. So theorem number 3. Suppose that Sn is increasing and not bounded from above. So if a sequence is increasing without bound, then it's easy to see that the limit as n goes to infinity of Sn, that this ought to be infinity. And now let's try to prove this. Again, the proof should involve the definition of the infinite limit. And for the definition of the infinite limit, what we need to do is to, given some number capital M, we need to show that there exists a capital N such that if n is bigger than capital N, then all elements of your sequence are going to be larger than the capital M that you had in the beginning. So let's do this. Let's choose capital M greater than 0. So then this capital M is not an upper bound of Sn, because we assume that Sn is not bounded from above, right? And if something is not an upper bound, then of course, what does it mean? If a number is not an upper bound, that means that we should be able to find an element of my sequence or of my set which is going to exceed this bound. So that means that there exists an n in R such that S with this index is going to be strictly greater or equal than, in fact, strictly greater than capital M. However, Sn is increasing. And if Sn is increasing, then surely Sn is bigger than S capital N, if n is greater than capital N. And then if Sn is greater than S capital N, and S capital N is bigger than M, it follows that Sn is greater than M if N is bigger than capital N. And what is the conclusion from that? That means that we satisfy the definition of the infinite limit. So therefore the limit n goes to infinity of Sn is infinity, and that's what we wanted to show. What's a symmetric statement to this one again? Let's make it theorem 4. So now let's suppose we have a function, a sequence which is decreasing and not bounded from below. What should be true about that sequence? Its limit must be minus infinity. The proof again is going to be a mirror image of the proof that I just did. So that would be theorem number 4. And so at the end of the day, then what do we know? Whether or not a sequence is bounded from above or not, the limit would always exist. It might be an infinite limit or a finite limit, but it always exists. Same thing for the sequence which is monotone decreasing and either bounded from below or not. If it's not bounded from below, the limit is minus infinity. If it is bounded from below, the limit is some finite number. So we can combine all these theorems into just one statement, and that is that any monotone sequence Sn converges. And when I say converges, I can imply either that it converges to a finite number or it converges to infinity. In the next lecture, I'm going to do a couple of examples. We'll demonstrate where this stuff that we just discussed is actually going to be useful.